Okay, so we're moving into section 1.2, and this is titled Solution Analysis. The first section had to do with drawing the molecular models, kind of that basic, and then it dealt a lot with stoichiometry. This is the solutions version of stoichiometry with some data that we can use. So question 1 says, what is the purpose of colorimetry? When should we use this lab technique? And when are we not able to use it? So for this one, write it up here first. Colorimetry allows us to determine the concentration of colored solutions. In order for this to work, the solution has to have a visible color. A colorless solution like water, not really going to work. So it has to be a colored solution. So look at number 2. Circle the compounds with which colorimetry would be a useful lab technique. So first off, aluminum chloride. Is it going to work? It says it's colorless. Not going to work. Calcium chloride, colorless. Not going to work. Cobalt 2 chloride, pink. It's got a color. This should work with colorimetry. Copper 2 chloride, it's blue. This one should work. Potassium dichromate, it's orange. Should work. Potassium chromate, it's yellow. It should work. Potassium permanganate, purple. Should work. Sodium chloride, colorless. No. Nickel 2 chloride, just nickel chloride. Green, should work. Zinc chloride, no. So anything on this list that has a color should work. Anything that's colorless, it's not going to work. So the question is, what do these solutions have in common? Some sort of a color. Suggest an explanation for the behavior of these compounds that make colorimetry useful. And this is a lot more technical than I would have expected in section 1.2. I'll just write it down and I'm not going to elaborate. So partially filled D subshells or sublevels. Think back to that ground state electron configuration that we learned back in Chem 1. And usually the transition metals had to do with the D sublevel. So they tend to have some sort of colored solutions. Number 3 says, state Beer's law. What factors affect the absorbance of the solution and why? Absorbance equals A times B times C. This is on your AP formula sheet. I'm going to make a note of that. So the absorbance, A, capital A, is the molar absorptivity, which is a constant, times B, which is the path length, times C, which is the concentration. You also have to know which wavelength. And remember, we looked at that graph. We'll see another one in a couple of minutes. We have to know what wavelength to measure it at for this to work. Later, I would go back with your AP formula sheet and fill in the actual terms for these letters. Capital A absorbance, that sort of thing. How do we determine what wavelength is ideal to use? So we're going to look so we have a graph. It's going to show us how it looks across all the wavelengths, and we're going to pick the one where the absorbance is the greatest. This is how we choose the wavelength. So without words, look at number 5 if you're done writing. We have this absorbance versus wavelength. We have all these different wavelengths. Which is the best one to choose? The highest spike in the graph. That's all you have to do. Find the tallest point, trace it down, and it looks about 580, 590.
Why would we not wear the wavelength where absorbance is 1?
Well, you could use it where absorbance is 1, but we're going to dilute this sample. So this is probably the full strength sample. We're going to dilute it anyway, so we want it where it's for sure going to absorb the most. So you've got this absorbance versus wavelength, and it looks something like this. Pick the tallest peak, trace it down, and on this particular graph, it's 580, 590. Question says at approximately what wavelength? You could say approximately 600 nanometers. You could say 580 to 590. They're all going to be pretty close. The absorbance is really high for all of those wavelengths. All right, let's stop before the announcements start interrupting us.